So today for the first talk, we have a presentation about Riemann surfaces and resolution of singularity, if I don't make mistake.
Something like that.
So by Marcos, just there. So we have 1 hour and 30 minutes for this presentation, and you are agree for we ask questions during the talk, so never hesitate to
interrupt.
Absolutely, yes. Yeah.
Thanks, and the floor is yours.
Okay, well, thank you. I mean, let me first begin by saying I'm not a historian of mathematics, so any historical comments I make will be probably very naive, and my main goal is to explain a little bit of the mathematics that was done around the time of Brill and Noether, partly by Noether and others. And the goal is not for me to just lecture to you. The goal is that I don't know exactly what you know, and the goal is to make sure everyone knows something. So just don't hesitate to ask questions and interrupt. I don't need to get to the end of what I've prepared. Okay. Okay, so I thought I would start. Let me just write down a few definitions before I explain what this picture is. I think probably a bit of light first, maybe. There we go. So let me first define what I mean by plane curves. So definition. So in general, we'll be considering polynomials, which are polynomials in two variables, x and y, and usually with complex coefficients. Algebraic geometers generally prefer to work with algebraically closed fields, but these pictures I show you will actually be over R rather than C, real coefficients. Then we can define the zero set of F is just the set of points A, B, and C2 such that F of A, B is equal to 0. Okay, so this is what we mean initially by a plane curve. Now, there's a special feature of certain points. There are a lot of, so in these pictures above, there are a lot of examples. In each of these pictures, there are certain points which behave somewhat differently than other points. And we can make that precise. So point AB in Z of F is a singular point if the two partial derivatives at the point, so at the point xy equals AB, and the partial derivative with respect to y at A, B, or both vanish. So we'll see this in a second with some actual equations. So roughly, the way to think about a point that's not singular, so a non-singular point, the intuition, a non-singular point on a curve has some kind of small open neighborhood in which you can view the curve itself as the graph of some well-behaved, say, differentiable function over either the x or y axes. Possibly both. This is a neighborhood inside the plane, yeah. graph of a function over either the x or y axis. So if both of these derivatives are non-vanishing, then you can take either axis. Otherwise, you have to take one of the two. So that's the basic intuition. So let me do some examples, and this is where I'll turn to this picture, which now somewhat awkwardly, I can't actually write on the board and display the picture at the same time. But I guess you can see the top at the moment. So as a first example, I discovered, well, maybe I should say a few words about where these pictures come from, because this is a historical comment. So this is, this is from a well-known book by Robert Walker on algebraic curves. It dates from, I think, the 1940s. He was involved in the story of resolution of singularities, which I'm going to talk about in the two-dimensional case. I'm going to talk only about the one-dimensional case today. He solved that problem in the 1930s. And this is the one thing I have personal connection to, which was when I was growing up and about 3 or 4 years old, he was this very kind elderly man in the department that my father was in. So I did know it, but it's, yeah, I had no idea he was an algebraic geometer then. Okay, so let's do a few of these examples. When I started writing these down, I discovered that he reverses the direction of the x-axis. So I need to, from the usual convention these days, I have to change a few signs. So first example is, well, right, y squared minus x cubed minus x squared equals 0. Okay, sorry, I'm having some, do we have other white chalk over there? Okay. Getting the pictures visible at the same time as the blackboard is a bit of a tricky exercise. So you can see here is at the origin, because the leading terms here at the origin are, well, it's y squared minus x squared. The partial derivatives will be linear terms which vanish at the origin. And so the origin is a singular point. xy equals 0, 0 is a singular point. And if you look at, again, at the leading terms, it's a good way to think about what's going on with the singularity. It's y squared minus x squared. And this factors as y minus x times y plus x. And you can see that in this picture. If you zoom into the origin, you'll see two branches. And those two branches of the curve have tangent lines given by y equals x and y equals minus x. And this is what's known as an ordinary double point. Two branches, each with their own tangent line. And so that is, now I need to find an eraser. Hoping it's over here too. Oh, yes. So this is something we call an ordinary double point. And these will play an important role in the story. So the second example is just a slight modification of the first one. I'll lower the board in a second. That is y squared, minus x cubed plus x squared plus y squared equals 0. Now again, all I've done is I've changed the sign here, so it's not going to change the basic behavior. But you will notice that the leading terms now factor not over the real numbers, but over the complex numbers. And this is now reflected in the picture on the right, which is perhaps a little bit misleading because the axes are obscuring part of what's going on. There's a point at the origin, and that point is isolated. So it's not the graph of a function there. You can see that very explicitly. And what's really happening is if you look at the set of complex points, complex solutions to this equation, you'll see two sheets, which are now two real dimensional, meeting in a four-dimensional space at a point. But you can't see that anymore in the real picture. So it is important to keep in mind that there's a complex picture here. Yeah.
Leading term is often the highest.
Okay, so here I want to think of a Taylor series expansion, and hence the lowest degree term. And indeed, so all these examples, the interesting singular point is the origin, so it's easy to do the Taylor series expansion. Otherwise, you need to sort of translate things over.
So it's unfortunate that we're looking at the real.
But we can't do anything more than that, of course. There are ways of thinking about the complex picture, but that's so far beyond. I think probably Brill and others did not have any such picture in mind. Okay, so the third example, this is quite a simple one. X cubed plus y squared equals 0. Now I can lower the backboard completely, attempt to lower it. These are not easy boards to maneuver. And that's figure 2.3 as the sharp point. Again, you can see sort of the key features in the real picture. And this is still a double point. So double point means that the leading order term is degree 2, but it's not an ordinary double point because it's a square, perfect square. A leading term is degree 2, but not an ordinary double point.
What of old was called the semi-cube book.
That's right. Yeah, so there are lots of names, many of which have been completely forgotten by modern mathematicians because we aren't so interested in the specific classification anymore. So for example, 2.4 is called the tack node. I could write down the equation, whether that's sort of that enlightening or not, I don't know. Sorry? Tack node, T-A-C-N-O-D-E. 2x to the 4 minus 3x squared y plus y squared minus 2y cubed plus y to the 4th equals 0. So you can see you still have a quadratic leading term, but again, it's a square. It's not. And the key feature of the tack node, so that's at the origin. There's a double point, an ordinary double point above the origin. The key feature of the tack node is that you have two branches through the singularity that are actually tangent. Two branches are tangent. I'll write down the equation for the fifth one and then stop with the equations, mostly because this has a delightful name of a rhomboid cusp. So we usually call, by the way, this is usually called cusp in modern parlance. And so the rhomboid cusp has equation x to the 4th plus squared y squared minus 2x squared y plus xy squared plus y squared equals 0. So again, it's a double point because we have a leading term of y squared, but it's distinguished from the ordinary cusp in that somehow there's some higher degree of tangency as you come into the origin. Okay, so this point, yeah, you can imagine there's some huge classification on double points. I don't really actually know where the story ends. But I think the other important ones to mention are 2.6 and 2.7. I won't write down the equations, but these are important examples for us because these are what are called ordinary double points. But this one is a triple point in the sense that the leading term is a cubic. And the leading term factors into 3 different linear factors, giving you 3 different branches with 3 different tangent directions. And this is a quadruple point, order 4, multiplicity 4. And again, actually, now that I look at this, I think it's not ordinary because it looks like the various branches are tangent there. So it's some kind of, I don't know what the name is. There's something. They do start looking like spirographs. So there's a lovely book, if you don't know it, there's a lovely book by Briscoe and Nur with a lot of historical point of view about singularities. And somewhere in there, there's some spirographs.
I think the fourth example you have, and next to last example, are multiple. Well, it's the problem of having a multiple tangent.
That's right, yeah.
And that's a real problem in resolving singularity.
Exactly, yeah. So we'll discuss these later. So I think this last example, again, I won't write down the equation, but Walker was making a point. This is actually, if in the real picture, this is actually a smooth curve, so you may not be able to detect the singularity just looking at the real picture. Okay, so that's what I wanted to do with these pictures. So that gives some flavor of okay, so we're actually now going to be interested in a more global question. So algebraic geometers generally don't like working, say, just with set of solutions in C2, because somehow we're missing these points at infinity. We would like, for example, all our curves to meet in the correct number of points, as Bazou tells us. And to do that, we need things like, well, parallel lines should meet at infinity. And that we do by introducing the projective plane. So I'll explain the projective plane as I do to my undergraduates. So the complex projective plane, normally in my discussion, I'll leave off the C, CP2, but how do we define this? Well, we take the C3 and we remove the origin. And then we divide out by some equivalence relation, where 2 points in C3 are equivalent if they are related just by common factor. So if you have this is equivalent to this, as long as lambda is a non-zero complex number. Another way to think about this is you just take all one-dimensional subspaces of C3. This would be a spanning set for the subspace. So projective geometry, again, because you're all historians, you probably know originated in the study of perspective, and I think the first texts go back to the 1600s in that context. So I'll write a point in P2 as by using kind of a ratio notation. Think of this as saying that what's being determined is the ratio between these three complex numbers. Now, the way to start thinking about the geometry of this thing is we like to sort of split it up into kind of a finite part that looks like the C2 and the points at infinity. So let's consider a subset. Just the set of points x0, x1, x2, such that x2 is non-zero. So I claim that giving a point in this is exactly the same as giving a point in C2. So notice x0, x1, x2 in U, x0, x1, x2. I can divide, because I'm allowed to multiply by any non-zero number, I can divide through by x2, and I get x0 over x2, x1 over x2, 1. And this is the unique representative of the point whose third coordinate is 1. Okay, so that means for any point in U, I can just write it as a tuple of numbers, and that completely determines the point if I set the third coordinate to be 1. So we get a bijection, roughly U is isomorphic to C2 in some sense. So what's left over, the complement of U So the complement of U is just the line x2 equals 0. And we think of this as a line at infinity. So if you're in real projective space, think of sitting just on a plane on R2. If you look off in some direction at the horizon, you'll see the point at infinity. And if you have two parallel lines in the plane, they'll meet at that point in infinity. And exactly this is how to formalize that. Okay, so maybe it's important to talk about what does it mean to give an equation for a curve. So what's important is if f is now a polynomial in 3 variables, I'll use variables x0, x1, x2. I need to insist that f be homogeneous. I'll say of degree d. So homogeneous means that every term is the same degree. In particular of degree d. Then if I rescale, so f of lambda x0, lambda x1, lambda x2 is the same thing. If you think about what happens, each term is degree d, I'm going to get d copies of lambda, and I can pull that out, and I get lambda d to the d times f of x0, x1, x2. So the value of the polynomial at a point is not well defined because it's going to change by value of a factor of lambda to the d, but whether it's 0 or not is well defined. F of x0, x1, x2 equals 0 makes sense as a statement for a point x0, x1, 2 in P2. And then, of course, we just define the zero set of F as being set of all A0, A1, A2 in P2 such that F of A0, A1, A2 is equal to 0. And now this makes sense provided that F is homogeneous, and this is what we call plane curve of degree D. So for example, if you take a homogeneous linear polynomial, that will give you a line such as x2 equals 0. Any two lines in P2 must intersect because you just have two homogeneous equations in three variables, so there is a solution. And therefore, if they don't meet on this open set U, they have to meet at infinity. So if they're parallel in C2, then they meet at infinity.
Intuition.
Yeah. That's right. So we need to actually be a little bit careful. I should probably insist that F be an irreducible polynomial to avoid having partial derivatives vanish. So for example, I take x0 squared equals 0. It's going to, the derivatives will vanish everywhere. And so then it looks like it's singular everywhere. But of course, as a set, it's just a line. That sort of is taken fully into account only when you get to scheme theory. So maybe I should just insist, let's take F irreducible. So we can't factor it.
But again, my point of intuition is you can sort of rotate the space so that your points are visible.
That's right, yeah. So exactly. So we always have, so any linear transformation on C3 will give you a automorphism of P2. And so if we only have a finite number of singular points we don't have to worry about, we can always assume they're visible in the finite plane, yeah. Okay, so then we can talk about singular points similarly. So point is singular in Z of F. Singular if all partials df dxi vanish at P. So again, it's not that hard to actually compute singular points. Yeah.
Yes, just for add something with your question and just for everybody can see what happens, is just first the singular point is isolate because we are on plane curves, but it's not the case for surface, for example. And we want to look at the projective plane for see what happens at infinity, because if you think about the inflection point, just y equals x cubed, and you watch what happens at the infinity, we have a cusp. Yeah. Because you homogenize, so you have y z square equal x cubed, and after you change and you appear at infinity. This is why it's interesting to always look at the curve in the projective plane, because we see that, in fact, if we see in the complex plane a smooth curve, it's not really smooth. Infinity possibly we have a singular.
Yeah. Yeah. I mean, this is also where I get on thin ice in terms of historical comments, but my general impression is that Riemann introduced the notion of what we call a Riemann surface. And these are supposed to be compact, we would now call them compact non-singular algebraic curves. And so particularly introduced the Riemann sphere. He said that somehow you're missing information. If you just work on C, for example, a holomorphic function on C might have some bad behavior at infinity, or a meromorphic function on C might have some interesting behavior at infinity. So he added an extra point to get the Riemann sphere. And that, of course, that's the same thing as CP1.
Yeah, but this, I mean, his comment, I think Klucker's formula is so much more relevant. I mean, that's pure projective geometry with duality. And so he was the first to figure out the tangential as well as the point singularities and how they play in. So that goes, I mean, Riemann and complexification and all of that, you go right into modern mathematics.
Yeah.
Your point was actually a classical point that was well known, that well before Riemann.
Right. Yeah. I mean, I guess I don't really know as I said, I'm not a historian. So, when I think of at least when I tell my class, why do I care about projective rings? Well, for example, Bezout's theorem is very important, and you can't talk about that unless you're dealing with projective things. Right? Things happen in infinity that you have to include, otherwise you don't get a well-defined answer. And indeed, if you really want to understand a plane curve and what it looks like, you're missing information if you look at infinity. So, one of the basic points, the remark I want to make is, in modern algebraic geometry now, we don't think of a curve as just being something sitting in P2. We think of some kind of abstract thing. If we really want, I mean, in undergraduate algebraic geometry, we'll define a curve as something satisfying certain properties sitting inside an arbitrary dimensional projective space. It has to be one-dimensional. My understanding of the history is that even the concept of dimension was not particularly well defined in algebraic geometry until after Brill and Noether. And it was easiest to just talk about plane curves at this stage. So that's a little bit constraining. And one of the reasons, there are a number of invariants you might be interested in in an algebraic curve. The very first of them is genus. And if you have a picture of a Riemann surface, then you can easily say, in some sense, it's not necessarily so easy to define, but the intuition is, well, it's the number of holes in your Riemann surface. So how do we detect, for example, the genus of a plane curve? So non-singular plane curve I'm going to show a non-singular plane curve of degree d. And again, this is in P2. This question doesn't make sense in C2. Degree d has genus 1/2 d minus 1 times d minus 2. So for example, degree 1 and degree 2, this is 0. So line is the Riemann sphere. Is conic is actually always isomorphic to a line. And so it starts to get interesting for d equals 3. And I always draw, again, this is something I always mention in my undergraduate class. So we draw, sorry, this is supposed to be a cube here, this is degree 3. So here's the finite real part of this curve. Will look something like this. Somewhere there's a point at infinity because these things go up. So the direction of this line gives you a point at infinity. So you can imagine this is kind of also an oval. And so you can actually see this kind of a slice of a donut, of a slice of a torus. So you can kind of visualize that there's some genus 1 going on. But the important thing to note is that we miss genus. I mean, there's no genus 2 curves in the plane as non-singular curves, and the gaps get bigger and bigger. So if you're only going to think about curves as things sitting in the plane, you are forced to consider singular curves. And so, for example, I don't remember what the name of this formula is. It might be Plöcker's formula. There is a simple formula for the genus of a curve with only ordinary double points. So if C is a plane curve of degree D, with delta ordinary double points, then the genus has to be modified. So we have 1/2 d minus 1 times d minus 2. These days, this will be called the arithmetic genus of the curve. And then we have a correction, which is simply we subtract off the number of double points. So another thing that I kind of wanted to talk about, but decided there wasn't really time, is what these days we call the canonical class. And in the old days, it was called the adjoint linear system. This was something that was can be defined intrinsically for a non-singular curve. Again, I think in Noether's time, it would be defined if the curve is sitting as a curve of degree D with a bunch of double points, the adjoint linear system. Let me attempt to draw something. It's not going to be a very good picture. This is a degree D curve. And then you would take degree D minus 3 curves passing through the double points. I don't know what those will look like. This is a D minus 3 degree curve. There's going to be some set of degree D minus 3 curves passing through the double points, unless D is 3. If D is less than 3, obviously this doesn't do anything. And the adjoint linear systems, well, you take a look at the points of intersection that don't include the double points. I'm not going to talk about linear systems. I had hoped I might have time to do that. But it's an important subject, which probably appears in the book too, but I'm not sure. Does it? Yeah. Do linear systems show up?
For sure.
Yeah.
That's major thing.
Yeah. Yeah, so this is certainly how it would have been defined. Yeah, so it's the notion of divisor. So a divisor is just a linear combination, abstract linear combination of points on the curve. So in this case, I would say, for example, we have 2 points here, and it's the sum of these 2 points. And then there's a notion of linear equivalence, which basically means that it's any 2 curves of this flavor would cut out the same linear equivalent divisor. So again, it doesn't take that long to build up the terminology, but I think that would be a different talk. And so this one was a very special one, which plays an important role in Riemann-Roch, for example. And one part of Noether's work, again, I don't know if it appears in the book, but is considerably more advanced, is he tried to do the same thing for surfaces. So for surfaces, you would have them sitting inside P3, again, a single equation inside of P3. And there are more kinds of classes that you would want to, and variants you'd want to define. And he did a very good job, actually, through very hard work, defining these things. In fact, I think even today to prove, it's sort of non-trivial to prove that it's easy to define the invariants in modern language, but it's then non-trivial to prove that he got them right. Okay, so this sort of explains various reasons why we want to consider singular curves, but also tells us that actually you really would rather have the singularities be as simple as possible, because otherwise you can't control lots of aspects of the singularities. So this brings us to resolution of singularities. Yeah, not green. So there are various ways that one can express this. In a sense, the simplest one for curves is the following. So given plane curve C, can one find, now I haven't actually defined all the concepts in this because we only talked about curves as things that live in the plane. So you have to accept that we can define the notion of a curve without necessarily sitting in the plane. So we could have a curve defined by a bunch of equations in a higher dimensional projective space. Can one find a projective curve not necessarily in the plane, C tilde, with dense open set, which is non-singular, and with dense open sets, U contained in C, V contained in C tilde, with U isomorphic to V. Of course, this contains a lot of concepts I haven't defined. I haven't defined what a projective curve means. I haven't defined what being isomorphic means, but hopefully you can forgive me that. Now, this was definitely not the question, as far as I understand, that Noether thought about. He's going to think about some questions I'll mention shortly. As far as I understand, again, historically, this was resolved a little bit later by, I can't quite remember who was involved, Kronecker or Dedekind, I'm not sure. But the key point that was understood a bit later on was that what really characterizes a curve is its field of rational functions, so functions that are ratios of polynomials, which makes sense if they're homogeneous to the same degree. And from the field of rational functions, you can actually extract C tilde. These days, we would just say, oh, you just normalize the curve, and that resolves it. And so it becomes an uninteresting question. It only becomes interesting in this degree of generality in higher dimension. So the second point is embedded resolution. And this is what I'll try to convey something about. So here's one way to express it, and I think this is more or less the way that Noether thought about it. Here we find a birational map. I'll define that in a second. P2 to P2. So what does birational mean? It means, i.e., f is given by some collection of three polynomials. So whenever I write something like this, of course, this allows me to plug in a point with coordinates x0, x1, x2. And as long as these aren't all 0, and as long as they're all homogeneous to the same degree, I get a well-defined point in P2. So this gives me a way with F0, F1, F2 homogeneous to the same degree. This gives me a way of mapping P2 to P2, but it could be these 3 polynomials have common zeros, in which case the map won't be defined at those points. So this is really a map defined on some subset, some complement of some 0 locus on P2. So that's the first requirement. That's what being a rational map means. And then being birational means it induces an isomorphism between some open subsets. Okay, so that's the definition of a birational map. So the question is, can we find a birational map such that the image f of c is a nice plane curve? Where nice means maybe just has ordinary double points, or maybe has just ordinary points. So ordinary, if you recall, meant that every branch had a distinct tangent direction. So the leading term factors into distinct linear factors. Okay, so that's one way of interpreting the resolution of singularities question. This is actually not really particularly the way we think about these things these days. So there's a slightly fancier way, and this requires knowing more terminology, so I won't dwell on it. More generally, can we find a surface S and a birational morphism f from S to P2 and a curve and a non-singular curve? I'll wave my hands at some of these terms in a second, but non-singular curve, C tilde in S, such that F restricted to C tilde as a map from C tilde to C is a birational map, so isomorphism open sets. Okay, so this requires knowing some things and some definitions that Noether probably wouldn't have known in the degree of generality that we're talking about. So a surface S now will be some abstract thing sitting in some high-dimensional projective space. A birational morphism means we have a map from S to P2, which is an isomorphism on some open subsets. And then, of course, we can find a curve C tilde, which maps down to C. So I'll try, if I have time, I'll do a bit of an example of this at the end. But what I want to talk more about is this first interpretation of what the term embedded resolution means. Somehow it's not actually, I mean, these days, when people talk about resolution of singularities, or embedded resolution, they always mean this last thing. And I suspect that these kinds of questions, like this first one, would be very difficult for higher dimensional objects, for surfaces and higher. Okay. So let's first look at an actual example of a birational map. Whoops, why did this go? Yeah.
Why do you think? I suppose that the first definition of embedded came before the second.
So, again, this is where I'm on dangerous.
I would like to get a feeling why people go to the second approach to embedded resolution.
Yeah. So I guess, I mean, for me, I would guess that it has to do with sort of the abstraction of going from thinking about curves or surfaces as just hypersurfaces, single equations inside projective space. And if you're going to think of those like that, you have no choice but to think of the first point of view. For the second, once you start sort of emitting some notion of curves or surfaces as living, as some kind of abstract existence away from just how they're sitting inside projective space, then this second question becomes more natural. So I think it wasn't that long after, I mean, certainly by the time, I think I wrote something here. Yeah, certainly by the time of people like Dedekind or Castelnuovo, that was probably how people were viewing things. But so the foundations of algebraic geometry took really a long time to develop. So and that's part of what's hiding this definition. When I say surface S, what do I really mean? And one has to have a notion. Certainly by the turn of the century, because algebraic geometers at least had some intuitive sense as to what they were. I read papers by Fano or Castelnuovo around that time.
We just had one remark about the point one that you discussed before.
Yeah.
You made a little remark saying, well, you just take the normalization.
Yeah.
This idea of normalization is only 1930s, 1940s.
Oh, okay, so even later.
That changed completely the way of looking at it. This arithmetization, I mean, inspired by Cruens.
Yeah.
It's much later. So, indeed, as you said, I mean, what we are dealing with falls under your point two and probably under its first interpretation.
You mean the projective curve that is not plane? Is that the one you're referring to?
No, what I mentioned for the first item, I said these days you just say we normalize the curve, which is some operation you can do to a variety. So I think the notions of the abstract curve, based on the reading I was doing this week, was somewhat after Noether, this notion of extracting the curve from by valuations of the field of rational functions. That wasn't that much later than Noether's work. But you still have to have some notion. It took a while to develop some notion as well. What do we really mean by an abstract curve? And in some sense, the formalization we use today for these geometric objects was really due to Grothendieck. That was much later. Okay, so let me try to give some concrete examples. So first, let's find an example of a birational map from P2 to P2. So the most famous example is quadratic transformations. And this has a very simple formula, is f of x0, x1, x2 is equal to x1, x2, x0, x2, x0, x1. So let's understand, first of all, let's see why this is a birational map. So of course, there are some common zeros. If 2 out of the 3 coordinates are 0, you have a common 0, and the map isn't a priori defined. So not defined at 3 points. P0 is 1, 0, 0. P1 is 0, 1, 0. And P2 is equal to 0, 0, 1. So that's the first thing to notice. The next thing to notice is that if none of the coordinates are 0, life is quite simpler, because I'm allowed to rescale. If the product of the 3 variables is non-zero, then I can rewrite this equation by just dividing through by that product. Divide through by x0, x1, x2, and this becomes x0 inverse, x1 inverse, x2 inverse. So that makes it obvious that on the open set where these 3 variables are non-zero, there's an isomorphism. You're just inverting the variables. Thus, f from P2 minus the 0 set x0, x1, x2 to P2 minus the 0 set of x0, x1, x2 is an isomorphism as claimed. Okay, so we have at least one such map. Now, it turns out that that's pretty much all you need to know about. And the reason is, also theorem of Noether and Castelnuovo, maybe before I mention that, let me do a bit more analysis. So we have lines. So if note a general point, i.e. not one of the PIs, on the 0 set of xi. So if the ith coordinate is 0, then, and the other 2 are non-zero, then notice what happens is that the ith entry up there is non-zero, but the other 2 entries become 0. So z of xi is sent to pi. So the picture is we have these 3 lines, z of x0, z of x1, z of x2. These are sometimes called the coordinate lines or coordinate triangle. We have these 3 points. Each of these 3 lines is contracted down to a single point, but different points, which makes it clear there's no way to uniformly decide where P0, P1, or P2 go. So it's clearly not defined at those points. Okay, so here is a fact. So you could ask, for example, you can compose birational maps. So the set of all birational maps from P to P2 is a group. Set of birational maps, P2 to P2, is a group which is called the Cremona group. And this is a truly awful group. I don't know how to describe it, but actually I can describe it very easily thanks to the theorem of Noether and Castelnuovo. What they showed is that it's generated by the quadratic transformation I wrote down and linear automorphisms of P2. So that's the group PGL2. It's 3 by 3 linear matrices act on C3 up to rescaling.
Is that a historical
Yeah.
question that we can say? You mentioned the book by Wiscon and Knotter, who of course refer to Knotter's result without, I think, mentioning Castelnuovo. You know, I thought that Knotter proved that every Cremona transformation is a composition of quadratic transformations.
So all I know is what my source said, which was, I think, Kolar's book on resolution of singularities. And so, yeah.
So there's some refinement at Castelnuovo.
I'm afraid I don't know, yeah. But the interesting, the reason why I want to make this little aside is there was very little progress on understanding this group until much more recently. So Giese-Thun, this was 83, gave a set of relations. Giese-Thun, Gizaatullin. So this was, that's, 1983, not 1883, so it's 100 years later. Actually, come to think of it, my source might have been Wikipedia, in which case you should say to take the claim with a grain of salt. But yeah. Now, I've certainly heard talks making various claims of this sort of as historical background and discussing the Cremona group. But as I said, I'm not a historian. And then, for example, Quentin and Lamy. And this was 2010, so quite recently, showed the group is not simple in the usual group theoretic sense. So as non-trivial normal subgroups. So this is the degree to which it's poorly understood is that it's taken, it's still an active area of research 100, however many 150 years later. Okay, so once we know this result, then this first version of embedded singularities becomes a bit easier to state, which is, can we, using a sequence of quadratic transformations, well, I'll now use quadratic transformation a bit more liberally to mean quadratic, the one I wrote down, composed with a linear change of coordinates. So I can choose any 3 non-collinear points as P0, P1, P2. So revised question. Can we resolve, again, put that in quotes, singularities by sequence of quadratic transformations? And so the basic idea is, of course, you might start with a very complicated curve, and we will try to choose our quadratic transformation cleverly to simplify the picture of the singularities. Okay, so let me do an explicit example of how this might work. Let's take C to be the 0 set of x0 times x1 squared plus x2 squared plus x1 squared x2 plus x1 x2 squared. Now, you can sort of see with, of course, you can all compute the partial derivatives and find out where they're 0. I'm not going to do that. But you can see a singularity lurking here, because if you look at the locus where x0 is 1, in that finite part where x0 is 1, you see a lurking term of x1 squared plus x2 squared, which hints that there's a double point at the point p0. We have something. And I actually tried to produce a picture yesterday of this and failed. I mean, tried to produce a computer-generated picture. But there's, if this is P0, I want P0, yeah, P0, there's some double point here. And then something else happens. Well, because I didn't manage to draw it. I won't do anything better than that. But there's one ordinary double point. Now you might say, well, now we're happy because that was our goal, was to produce something with ordinary double points. But we can do better. We can actually get something non-singular. So let's see how that happens. Well, I mean, one way to think about this, I was a little bit dishonest when I said, well, we just take the image of C. The problem is the map, F, is not even defined on all of C. It's not defined at P0. So what we actually do is we take the image of all points where the map is defined and then take the closure. And it turns out algebraically that's very easy to do. All we really have to do is write down the equation for the image using this equation, this version x0, x1, x2 goes to x0 inverse, x1, x inverse, x2 inverse. So let me write it like this. So point x0, x1, x2 goes to the point with coordinates y0, y1, y2 being x0 inverse, x1 inverse, x2 inverse. Yeah, question. Yeah.
At P0, we don't have a double point because in fact we have a double tangent. In fact, that's cross, but that's close to.
Let's see, did I mess this up?
I think no, we just arrived. We have.
So let's see, when x. Yeah.
In fact, it's only singular point.
That's right, yeah.
If you take x1 equal 1 or x2 equal 1, then you have x0 plus something. So when you derive by drawing x0, that you have 1, so it's always smooth. But at P0, you have each time the both derivative will equal 0.
Yeah.
The singular point at P0. But what happens at P0, it's I think you have effectively something like that, but you have not a cross. In fact, you have something really tangent at the end, so not something like that.
Well, let's see. So we have x, I mean, the local behavior is x1 squared plus x2 squared equals 0. So that's like one of our bad points that in the second figure of Walker, where we just, if I drew the picture, it would really just be a single point. So this is a very bad picture. That's why I failed to draw the picture. So we actually have complex branches. Depends what you mean by bad. Yeah, of course.
Please, please.
Yeah.
Stupid
And there's no
people
stupid
are
question, yeah.
Welcome,
So
encouraged.
you defined one quadratic transformation, and essentially it's kind of involutive, right?
Yeah.
So what's the sequence of quadratic transformations?
Oh, okay. So something I said but didn't write down was I'm going to use the term more generally to mean the one I wrote down composed with a linear transformation. So that allows us to actually choose P0, P1, P2 to be any non-collinear points.
Feel for me of untangling these bad things.
Exactly. Yeah. Yeah. Okay, so doing this computation in practice, what this means is I can write down an equation for f of c in the y coordinates just by replacing each xi by yi inverse. So I get f of c. I get the slightly nonsensical So this only makes sense when none of the yi's are 0. Otherwise, this is not a legitimate equation. However, I could multiply through by something. And in this case, I'm going to multiply through by, again, I'm free to do that if none of the coordinates are 0. I can multiply by some collection of the variables. Let's multiply by y0, y1 squared, y2 squared, and we get f of c is equal to z of, so I cancel the y0, I'm going to get y2 squared, plus y1 squared. Here I'm going to get y0, y2, and here I get y0, y1. Now, I could have multiplied by some more complicated monomial without destroying this equation, but then this would be reducible. It would have a common factor. If I had an extra, say, y0 in there, I could factor out a y0. So this is the smallest degree monomial I can multiply to clear denominators. And lo and behold, it doesn't have a common factor y0, y1, or y2, and this actually is the correct answer. And this is a conic. And easy to check is non-singular. Okay, so that shows how things work, at least to some extent. What I understand, again, this was drawn from Kolar's book on resolution of singularities, where he starts with something like 13 different proofs of resolution of singularities for curves. And it talks about Noether's proof, among others. Kolar has a book on resolution of singularities, and it's certainly not a historical book. Its aim is to, sort of graduate level text to actually explain resolution of singularities in any dimension, but he begins very gently with, you have to understand modern algebraic geometry, but he explains, translates into modern terminology what some of those older proofs were. And in particular, he talks about Noether's proof. So I outline Noether's approach. Yeah.
In this concrete example, can we repeat what we are doing here precisely? So we start with a curve,
Mm-hmm.
and this multiplying, this is resolving the same.
So the problem is we're trying to understand how to compute the image of the curve. And if you recall, let me try to draw a picture of this. So we have these two triangles. I'll draw F here. Actually, I should draw it as dotted to remind us that it's not defined everywhere. So the complement of the triangles, f is an isomorphism. So I can describe the equation for f, for the curve, here, which I've done because that's how it was given. And then as image, I can describe away from the triangle by just replacing every variable by its inverse, because that's what the map does, is it sends each variable to its inverse. So that gives me a nice equation, but it's not an equation for a curve in P2, because it has all these inverses. So then I say, well, okay, I'm free to multiply by monomials, because the worst that will happen is I will do something funny on the boundary on this triangle. And so let's multiply by monomial, the smallest possible monomial, smallest possible degree monomial in each variable, which will clear the denominators. And that's what I've done. If I multiply by too much, I would have an extra factor, like y0, say, and that would mean I've gotten I've gotten a reducible polynomial, and we want an irreducible polynomial. So that's the algorithm.
So that you can look at the curve in a nice way.
That's right. Yeah, it's clearing denominators.
Yes, you.
Okay. By the way, I took this from our Part 2 algebraic geometry homework sheets. So. Okay, so Noether's theorem in this context there exists a sequence or a composition f p2 to p2 of quadratic transformations such that f of c, so we fixed a curve c, f of c has only ordinary singularities. I think, Paul, you said the other day that Noether actually got the statement wrong, that he said that he could get ordinary double points. Is that what you had?
No, in fact, obtained that we have only ordinary singularities, but he said that he can also obtain double.
But didn't give the proof, or?
But he never.
Okay. Margin was too small, something like that. Okay, so for many purposes, this is actually enough. So things like adjoint linear series can be defined fairly easily, or for that matter, the genus can be defined for ordinary singularities without too much effort. In fact, I'll show you a formula for that. So I'll just, I don't have much time left, so I'll give a sketch of the proof. So what we need to pick, so fix C. So I want to simplify the singularities of C. And this is a universal issue in all questions of resolving singularities, is we're going to do some operation. And we need to understand what does it mean to simplify the singularity. And if you don't have a good measure of simplification, you're going to be in trouble. So let's let P and C be a non-ordinary point. So a point we want to make nicer. And then take, or let's call it P0, and take P1 and P2 not in C general. When I say general, I mean they shouldn't be on a line. So I can define a quadratic transformation. Yeah. Sorry. They shouldn't be on a line. I'm not sure how much more general. So one of the difficult things about reading classical algebraic geometry is the severe abuse of the word general. And which is many theorems that were proved, and I actually ran into this problem reading Fano when I was working on my PhD thesis. They state things without really explaining what general means. And in particular, you don't really know if the property they want to hold actually holds for, say, most choices. But anyway, I don't think this is a particular issue here, but probably all you need is that they shouldn't.
Non-ordinary singularity.
That's right, yeah. So for example, a Ramphloyd cusp or any of those other more exotic ones I drew pictures of. The one that we want to get rid of.
The conditions P0, P1, P2 are not.
That's right, because otherwise we can't actually define the quadratic transformation. And it's possible we need something more. Maybe we want the lines through them to be otherwise transverse to the curve. There are various things you can imagine. Everything, all the sins are hiding in the word general. So let F be the quadratic transformation. And I'll just use this word with centers, P0, P1, P2. So you want take a linear transformation that moves them to the coordinate points and then apply the one I wrote down. Okay, so it's sort of clear we have to do something. We have to, one of the singularities has to be one of these points. Otherwise, we're probably just going to mess things up more. So then the question is, how can we measure whether things have improved? And so one defines the notion of the apparent genus of C. So it's given by the following formula, 1/2 d minus 1 times d minus 2. So that's what the genus would be if it was a non-singular curve. But then you subtract off the following quantity, summation over all singular points of the curve. Sum is over all. Singular points, and mi is the multiplicity of the ith singular point. The multiplicity just means if you do the Taylor expansion at that point, it's the degree of the lowest order term. So all the double points are multiplicity 2, the ordinary triple point is multiplicity 3. So if all the points were ordinary, this would be the genus of the curve. The points need not be ordinary, so this is a slight miscalculation. Okay, so then one has to show two things, which I'm not going to do because I'm out of time. But first of all, the apparent genus C is always non-negative, so it can't go below 0. And 2, GF of C decreases after performing the above, the quadratic transformation. Now, both of these things are fairly easy to prove in modern language, and I think Collar's book gives a proof in about a page. I have no idea how Noether did this, but it is somehow still, the basic idea is still fundamental to any sort of approach to resolution of singularity. Somehow you have to get some measure of badness of the singularity and something, so that's
Can you give a hint about this? Because I mean, that's just a sort of formal thing.
That's right, yeah.
Another question in relation to this. I'm curious to hear more about this notion of apparent genus.
Yeah, so I don't think I have that much more to say, because somehow I think it's the reason why it works is buried in the details of the proof, which I didn't prepare. I mean, if you want me to give another talk, I could, but it will get harder because I have to use, I mean, I really will not be able to read Noether's original proof, so I would have to give a modern exposition.
You have the parentic genus just for. Like,
No, it's very interesting, the notion of apparent genus, which is precisely the one that is going to be modified so that you get to the real genus.
Yeah.
So I find this is very interesting.
Yeah, so in modern language, so this is not quite, so as I mentioned that this quantity would be, if we erase this would be the arithmetic genus. So that's something you can define in modern language. If all the points were ordinary, this would be the genus of the resolution. So there's some correction term for the non-ordinary points, and that's really what we're going to be capturing. Again, I don't, without getting my hands dirty into this proof, I can't really add more insight into what he was thinking. But I do want to emphasize that this idea of having some measure followed by is crucial in all these arguments. Maybe just end by saying so the study of resolution of singularity is still very active. So in characteristic zero, so working over C, singularities were resolved completely by Hirodaka in the 1960s. In this immense paper that essentially killed the field because it was virtually impenetrable. It meant that everyone out practicing algebraic geometers used it as a black box and never actually, I mean, very few people actually ever read the proof.
Is that that submission?
Yeah, that's right. That's where you. Okay, it's just a sum over all singular points. So let's label the singular points Q1 through Qn. That would be 1 to n. Yeah, so starting in the 1990s or early 2000s, people started going back and finding simplifications of the proof. And there is now work where the proof has gotten simple enough that it can more or less be delivered in 2 lectures. So it is a good example of how work can really be simplified over time. So I'll stop there.
It's 11, so now it's time for break, but we can take one question. Yes, yeah.
Well, I have a small clarification about this formula and then a more general question. If by performing the transformation, you're removing singularities, and this term is a negative, wouldn't it?
Okay, so afterwards it will. So the degree can also change. So there are a lot of things that can change here. So as I say, I could actually prepare more if people are interested, but it's a slightly complicated.
For you, possibly for other people in the room, do you know where the interest in studying these resolutions of singularities, what the motivation is? Just some kind of like, oh, we have interesting points of these curves, can we get rid of them? Or
So Yeah, so it's really kind of fundamental. So the received wisdom for probably well more than a century was that you really don't want to think about singular varieties. There are a lot of things that are easy to do on non-singular varieties and become very hard to do on singular varieties. And therefore, the best thing to do is if you give me a singular variety, the first thing I want to do is resolve it. That's changed a little bit in the sense that these days there are classes of singularities, of well-behaved singularities that we like to use also. But any kind of study, including dealing with those singularities, is fundamental to have resolution of singularities. So the fact, for example, that resolution of singularities doesn't exist in characteristic P means there are lots of theorems we would like to have exist, don't.
I think it's a topic too that has a really long prehistory, and I mentioned the Tooker formulas, and that he takes the simplest singularities for those, right, which for a long time that was standard, so double points and cusps, and then they have dual singularities, and so you get these beautiful formulas, which I think people didn't call themselves algebraic geometers back then. Of course, they were just doing geometry, but that was, I think, a point of view that held out, and the birational geometry and genus and so forth uses those, to begin with, use those same singularities. So basically, the genus is the formula you gave minus the number of double points minus the number of cusps and so forth, but it's a birational invariant and not a projective invariant. So these things are old and go way back, and then the problem, what do you do with higher singularities? Well, then you begin this industry of tricky stuff that keeps going on, but it has a really old.
Yeah, I think the translation that you sent me of the chapter on Noether said that sort of, previously people just always assumed that the singularities of these curves were nice, but of course in real life you can't just make assumptions like that. Again, that sort of has a lot to do with this misuse of the word general in classical algebraic geometry.
Reply to your question, answer to the question is the Flickr formula or the formula of the genus that we know for nice curves, but what happens when the singularity looks really bad? Just we want to reduce the type of singularity, but have something simple, and because it's invariant, transform irrationally your curve, that's the genus never change. This is why with the quadratic transformation it's good because it's irrational transformation. And so I just want to generalize or just want to have more curve for one table, just have another one with the resolution.
Yeah, and just to emphasize what I said from point of view of practicing algebraic geometry. Yeah, you had a question too. Yeah.
Please, can you help me differentiate between the singular points and the non-singular point through an example?
Yeah, so I mean, we could do. Let me go back to the first example I wrote down. Which was y squared minus x cubed minus x squared equals 0. So, I mean, maybe we should do the exercise of actually identifying some singular points. What we do is we differentiate this equation with respect to x and with respect to y, and we want both of these derivatives to vanish. So that would be 2y minus 3x squared minus 2x equals 0. And that's the, sorry, I can't differentiate it. I mean, just the x derivative is that. And then the y derivative, I was getting worried because that looked pretty hard to deal with, is 2y equals 0. So, right, so I want to solve these two equations simultaneously. Well, actually, these three equations simultaneously because I need a point on the curve. So y equals 0. So if y is equal to 0, then we have x cubed plus x squared is equal to 0. and 3x squared plus 2x equals 0. Now, this is a polynomial in one variable, and this is its derivative. And one way to think about this, these will have a common 0 if there's multiple roots, which in this case is x equals 0. So x equals 0 is the only solution. OK, so that's identified the singular point. So now let me just draw the picture. Different color here for the. So you can see at the origin. I don't know if that's visible there, but yeah. So you can see at the origin something funny has happened. And that's precisely capturing the fact that you don't. So at any other point, so I made this point that other points, that's non-singular points, you can view this as the graph of a function. So let's look over here. I can actually solve it for y in terms of x. Y is equal to, use white for this. Yeah, sorry, did I do something wrong?
In the other, not like that.
Oh.
Because if you make y equals 0, you have x equals -1.
Okay.
Sorry.
It was too beautiful. Oh, yeah. So the problem was that I drew something on here. I think I realized after I drew it that he was using this different convention. Anyway, yeah. Key point doesn't matter that much. So if we look over here, I can actually think of this. Let's just solve for y. So y is equal to square root of x cubed plus x squared. So I'm choosing the positive square root here. And this is a graph. So this is not the kind of function we usually admit in algebraic geometry because it involves a square root. But it does describe this as the graph of this function. Similarly, over here, I obviously can't describe it as a graph of a function over the x-axis, but I can think of it as a graph of a function over the y-axis. So here I can solve for x in terms of y.
I'm sure you would prefer to do it for x positives.
Yeah, so what's the solution? I suppose that I probably need to.
Doesn't matter.
Okay, yeah, okay. Sorry, I didn't prepare this. Yeah, anyway, so but over here, there's no way I can describe it as the graph of a single function because there are two bits passing through. So it would be multi-valued. Yeah, I don't just.
Thank you.
Anyway, yeah.
In some sense, the whole point of this whole endeavor is to find an advantage in projective space where crossing of the curve of itself is not a crossing.
That's right, yeah.
Rotate your ambient space.
Yeah. Yeah, so the thing I didn't get time to talk about was blow-ups, which would be so the second point of view on embedded resolution.
We need to stop.
Yeah.
But, speak a little bit of the blow-up in the product transformation.
Thank you so much.